Yeah, so he's seen that. Let's just tell this one. Point. I know it's like all got adrenaline coursing through your veins, and it's like enjoy the feeling because that's what life's for, right? It's exciting and scary, and that's how new stuff happens. So let's spin the wheel and see okay. And then
I can maybe also come around here so you're not standing in front of the screen.
Actually, no, he needs to have audio on.
I guess.
Yes. But I'm just thinking we don't have
Okay, you're all good.
Where do you want me to stand?
Yeah, I would put that on top of that laptop and stand behind the podium.
Remember, he has a screen share.
He's screen sharing.
I am screen sharing.
That is not screen. Is it green button inside the Hangout tab?
Maybe you need to mirror. You're probably sharing this screen.
Okay, and then just
Do you see that?
No, I see the Hangout tab. All right, I'm trying to get
Mirror.
Yeah, I think you need a mirror.
What do you see now? Let's try again.
One, I guess.
So whoever's voted for this team doesn't count.
So I think you need to be mirroring and then sharing your screen.
Right, I'll unshare and then mirror.
You need to hit share in that window.
Yeah, I've done that. Okay. Right, so I'm sharing now.
Yes.
Yes.
You see it.
Then I go into PowerPoint and do that.
We're in.
Okay.
Win.
Ready?
What are you seeing now?
It's perfect. We just need to get rid of the little window in front. Excellent.
We're all good.
Excellent.
Good to go. Hi, we're the Unwell Hackers. We are a combination of Teradata, Think Bigger, Teradata Data Science, and our new friend James from Glencore, who has provided the data for this. We've been working on some petrophysical data in the form of last format well logs. The problem with working with well logs is if you've got lots of them and they have gaps in either for data quality reasons or someone didn't log or you had a borehole collapse, make up the data that should go in that place by some kind of predictive modeling. Some software packages do this better than others. None of them do it perfectly, and there's certainly no coherency to the workflow. And you don't get to choose which mathematical algorithm you want to use. It's very difficult to do this kind of thing at scale across the whole basin, and you don't get the audit or governance you would require to be able to find out what someone did a decade ago. To be able to do is automate all of this data loading to apply some decent governance to it, use some existing curves to then develop a predictive model, so a bit of data mining, a bit of machine learning, be able to do this either at the formation level or by geographic subsetting if you want to use that particular day of the week. We would then like to be able to predict those sections that are missing and retain all of that information for when we want to apply it in a real business sense. For those that don't like words and prefer pictures, that. We've got a couple of curves missing from our wells. We'd like to be able to apply some kind of function, gardener's function or whatever, and be able to put ticks in these boxes to say, yes, we have a basin-wide data set for all of the parameters we need, and whatever rock property modeling tool we want to use. So, section. We're first and foremost a data management company in Teradata, so we like our architectural diagrams. This one takes, and this is all open source, we're not trying to have a proprietary little hackathon here. This is out there on together. So, last files sit on your staging server. It goes through Kylo, which is a wrapper around the Apache NiFi. Data governance, we get the data lineage coming in right from source file into our data lake. FS as our data lake. It's easy to use. We parse out the last files into 3 types of table: the well headers, the curve master, and then the measurement data itself in the curve data as a long, thin, skinny table. So we've got 8 nodes, so we can parallelize this, and the data ingest and the processing is very scalable. 3 6.2 wells, half a dozen logs for each well. This got pushed in a couple of seconds. So from there, we want to have a lightweight relational view on top of this. For this, we use Hive. That gives us grown-up database style orchestration and lineage. And we can access this through RStudio server. Everyone here knows R, much better than myself, I guess. And we can then put in the modeling functionality that we would like to use as a set of R functions in here. We can then develop further using the Shiny server application infrastructure, or when we've got the application hardwired or ready for use, we can push it out to something in the productionization world. We use Spotfire for that. So, mock-up of the front end, we never quite got that working, but we did manage to put in a machine learning button, push that, we do machine learning. Does it work? Yes, we took it out, went around the back, threw it back into Excel, and we got a squiggly line on the squiggly line, so we're really happy with that. And we've got all of the benefits we wanted: a repeatable and auditable. It gives a consistent, coherent data set, and we reckon that at the scale it works, at the speed it works, that we can enable more robust modeling. Thank you very much. It was awesome. Yeah. Questions from the judges to the rest of my team who are dotted around.
One question: how does speaking work?
I don't know, I only arrived this morning. Stand up to the team. We've got data engineer, data management specialist, subject matter expert, and front-end GUI guy. Yeah. 2.5 minutes.
So my question would be, so you're replacing the equations, so what's the added value of using some physical model?
The standard transfer.
I think that's one of the key ones. You've got the lineage. So if someone worked on it a few years ago, you're not spending a week or so going back through it all before you can trust that and then take it forward into whatever your new workflow might be. You have all of that provenance around it, you can hope.
That's next.
Good. Oh. Yeah. So, well, I can see some code repository where you might build those transforms out either on your own intranet or out there in open source land. And then these are all open source as well, so the ingest, that can only get better and more functional as people add to it. NiFi is already out there with this base functionality in it. So being able to do it at speed with the robustness and with the functionality.
And that's it for questions there.
Okay.
Thank you very much.
Okay,
Oh, that's
awesome. And the green screen share button.
Yeah.
Do we see that? I don't think you could see that.
Yes.
Yeah? Okay, we're off. Marine, everything's good?
Roll timer.
Let's do it.
Okay, we're Team Janos. Janos is a Roman god of proper decisions, and we want to make the proper decisions with our machine learning algorithm, so that's why we call it Janos. So the basic idea is you have some kind of cross sections, and you invest time and money to get some cool 3D model from these cross sections, and it's a very hard process, as you all know. For the course of this hackathon, we broke it down to a similar problem. So we just said we are going to make the 2D case. So you can imagine you have two welds, for example, one on the left side, one on the right side, and usually the modeling softwares, 3D modeling softwares that we know, or 2D modeling softwares, are just interpolating with a linear section, and that's probably not what you want to have. Then you can apply like DSI or some geostatistical stuff, but you have to have a lot of knowledge until you get something like this, to have something like a valley here. And we want to have an algorithm which can, predict from a lot of welds, something like that. So what we did, we already had a free model ready, which was from Lower Saxony. And from that, we wanted to generate boreholes or well data and use this as a training data. And we also wanted to generate cross sections, and then say we can use this for the validation of the model. So then we started working yesterday, and we found out, okay, our model is probably not that good because we don't have bodies. We just have horizons, like flying carpets around. So it was quite easy to generate the boreholes in the first place, but it was quite hard to transfer them for the machine learning algorithm. So there was quite a lot of problems we had to face. And then we said, okay, we want to generate these cross sections. Problem was with the cross sections, they were not colored, and so we couldn't use our validation algorithm, which we have, which is comparing pixels of the images, and then says, okay, you're right or you're not right, and then we have some kind of percentage. But because we had this bridge to gap and we couldn't fill the gap, it was quite hard in the end to overcome this. Yeah, what we have as a result at the current stage. So we see this is the cross section we wanted to predict. We had like 3 boreholes in this case, and we see this blue thing is a salt dome, which is for us the interesting thing here. So it's a nice geological feature, and this is the outcome. We see it's a bit different. We don't match the colors yet, but some general things are there. So if you see like this formation cropping out here, you have this here. So the scale of the picture is not the same. It's another problem we faced. We have this on the other side here also, and the green thing is similar to the yellow thing. It's a bit turned around, but it's already there. So yeah, it's a way to go. What is our team? And yeah, that's it actually. So we were working with Hawaii, who was not here, and he did all the machine learning stuff. It was great, and all the others did some GUI stuff and yeah, generating of data. Okay, that's it. Thank you.
So what are the next steps?
Next steps. We need more data because now we have figured out the format between the machine learning guy and our stuff. We need to pick the proper sections, which is okay. If you want to predict the salt domes, we were told that we might have salt domes in the sections and also in the boreholes as well. So we have to look at the data again and pick them properly. So we have some kind of human interaction. And with that, we can have a better training, and then in the end, automate the whole process. So right now, this is more like 3, 4, 5 strips. Everyone was running it, and then delivering the data to the next guy, to the next guy, to the next guy. So there was some, let's call it back at the moment. Yeah.
How was it managing the remote collaboration?
It was sometimes quite hard because face-to-face talk is sometimes easier. You can get rid of misunderstandings quite easy. Because you can just draw it on the board and stuff. and you have different times when you go to lunch, and it's easier. But in the end, I mean, like today we managed it. So for a real workflow, you need some time to set up this whole thing. And I say now we have a clear format, and now we could really work. Well, time's up.
Or maybe the question on the commerciality. In the presence of seismic data, how do you see the value of this?
I think in general you could input anything there, and then have you have to provide some interpretation, because we did just the stratigraphy from the 3D model we already had, and you have to say, someone has to say, okay, these sections or these parts of my seismic section are related to some stratigraphy or lithography, and then you can run, I think, the same, basically, just some work.
May you say a word about the architecture of your solution?
Architecture of our solution is not very complex, just like 3 Python scripts. So we didn't use anything in the cloud or something like that right now, because we didn't face too much of data. We have the 3D models in a database already where we generated sections in the boreholes. So this was quite easy, but the other stuff was more like, okay, we give you the data like that.
Time for one more question. Short one. Where was Poway?
Poway was in Aachen, actually.
Ah, okay. So you know him in Meetspace?
Nope.
Oh, okay.
No. First time meeting him here.
Okay. Okay. Well, there's no more questions.
Good job.
Awesome.
So keep submitting your votes.
Thank you.
Team Think section is next.
Yeah. It's probably
Looks good.
There you go.
You're in.
awesome. Thanks, Simon. It's there. So they're switching halfway through, you know that? They're switching laptops halfway through. We won't do the rigmarole for the second one.
Oh yeah, so it's my fault. Okay.
You ready?
Okay. So our team is called Think Section, and so we are working on quite a different scale. Polarizing microscopy, some of you people probably know it. It has still a lot of application in industry
and in research, of course. Strangely enough, it's still quite an analog business, and that's partly because these sections contain so much information. It's hard to get them into the physical, digital domain. Sorry. So a few years ago, we tried to change that by building a microscope that can actually do that. And I brought some data from that microscope that we're gonna then, try to harvest with some machine learning. And Brendan will talk about that later. I'll just quickly show you the data. So that's a thin section of sandstone with some pores that are stained with fluorescent epoxy. So as you can see, we can go anywhere in the thin section at quite a resolution. We can switch from plain polarized light to the fluorescent imagery, zoom out, go anywhere. So it's kind of like 200 gigabyte of raw data in here that's being processed. And we can also change the polarization everywhere. So we have a full stack of polarization, a lot of information, and we're going to harvest that with machine learning. So yeah, and that's a workflow that we're going to look at. So these 18 polarized layers, 1 unpolarized layers, and 1 fluorescence layer. We're going to do segmentation, clustering, classification of that, and that's where I want to.
Great, thanks, Simon. So yeah, Simon brought this data set, and as you can see, it's got a lot of rich features to use for classification and clustering. The problem is, with 200 gigabytes of images, that's a lot of pixels. So the standard approach of just taking all the features for 1 pixel and trying to find a class for it means you're going to be there for a long time. So we came up with a way to actually make that a more efficient process. So the first thing we did was a segmentation process. So a lot of these regions, there's sort of grains that are more than 1 pixel big. And so we have a segmentation process using super pixels, which are like pixels just better. And what that does is it finds a neighborhood of pixels that are similar in some sense. And so in this case, we're using all these features to determine how similar the pixels are. And so we'll draw a little region that represents a group of those pixels, and that's what we're going to use for the next step, which is clustering. We're going to then, across the entire image, find all the super pixels that have similar features. Okay, and for each of these regions, we're calculating a number of other features in addition to the ones we already have. We're going to calculate textural measures. We're using hair look features to analyze sort of the grain patterns in there. There's a lot of computer vision techniques that we can use to analyze the texture. Once we do that, we've clustered all these to find groups of these super pixels that are similar. Then the geologist can come in and decide which one of those groups belong to which grains. So the geologist can assign grain labels like quartz and so on, and pores, and then we can further analyze them. And so Diego is going to wrap this up by showing how we took this and made a web application out of it, or a prototype web application out of it, that will allow a remote user to connect to a large data set and kick off their analysis process.
Right, so we are able to load an HDF5 file that contains many layers of the sample that Simon showed you, and you can basically help through the app. You can classify the k-means image that you saw, and after you're done, you basically call in the machine learning classifier and get the classified image. And so this is live. This is actually doing all the things that we described, and it's very modular, so we can actually add in more features in the background. And time's up.
So did you guys know each other before, or how do you set up for this topic?
I mean, everyone knows Brendan, but not because he is now a machine learning reference in geoscience. But we had never worked together. No. Yeah, this guy are also part of the team.
But otherwise, we met here for real. I mean, they all. Yeah. You know, I knew of some folks from the online forum before, but I hadn't met anybody in person ever.
So what's the plan with this app?
Well, I guess the last bit that I was going to mention, the idea is that you can download a classified model that, in theory, for example, this was done on a very small sample. So with a trained model, you could potentially do these classifications for this kind of data
We're showing
any
one
levels.
tile here. This complete image is composed of a number of these tiles. And so the way we did it, you could apply that classification to all the tiles in the entire thin section after you've done one and get a classification of it.
This has wider application like vegetation and land use.
Sure.
Anything that comes with a rasterized set of spectral imagery.
That's right. Any hyperspectral image, you could use this for that approach. Yep. Yeah, that's right.
Very good. You have time if you want if you have another question.
Anybody else?
I mean, it would be also cool to build an API.
Yeah, you
like,
can do
so
some
that
analysis on
anyone
it
can-
too. This last slide here shows just one grain type, I think the quartz grains, and it's showing various, it's the aspect ratio of each, the major and minor axis of each grain. You can analyze pore space, for example, would be important in oil and gas, to analyze, the shape of them, the aspect ratios, and so on. So that's what that last image does.
Do you have a plan to keep on working together?
Yeah, we've actually already been talking about that. Simon can use this for research. I have a project I'm working on analyzing actually core images from the big core, and I want to use it to analyze the bedding and so on in that. So absolutely. Diego's talked about using this for astronomical images as well. So.
So, welcome to everyone. Thanks for bearing with me in the Google Hangouts. I think it's going okay.
Team Classy's up next.
Team Classy.
So we are Team Classy. That comes from classification. The name of our project is Seismic Shotgunner Interpreter. Where, we'll see what it's about in a few moments. So we are 5 people, but Tom had to leave yesterday quite early, and Justin is doing that from Houston. I guess he's watching it now, but we had to pull his image from the web. So, okay, a quick introduction. We have a shot gatherer, and before we jump into heavy processing, we want to know what it is showing us. Really briefly introduce the event, so we want to know what there is this wiggle. And ideally, we want to say, okay, this front roll, some kind of noise airwave, have reflections, whatnot. So we want to classify this events on our seismic shot gather or common midpoint gather. So our approach is simple. We take a shot gather, we make a transform into another domain where we can actually see the events as dots that we want to classify here based on where some features, right? And then we want to display a kind of graph of what this event is. So it shouldn't be precise. It's not picking. It's just a very simple pointing to what kind of event it is. So, of course, running the whole process will be an enormously difficult project for 2 days. So we just focus. Saying we have data already here in this domain, nicely separated in points, and then we can work it out from there. So in a sense, we had to skip physics a little bit, but this can be further improved later. So that's a short layout of what we did. So we generated this set in this domain, transform domain. We trained a classifier, which is a support vector machine classifier. The labels were there when we trained it. Then we did the labeling for the data. So in the sense, it is a kind of first problem, right? But yeah. So let's see now how it actually performs. We did have time to run into some troubles making the nice interface, but for now, again, it's a very toy problem. So we specify a number of different events. Again, forget about physics for a little while. Say, if I say I have 2 primary 15 reflections to some noise, coherent noise event, and 5 of a multiples, this is what I get. My seismogram, I want to get this, so different colors, different events, and this is what we get as a prediction. Here is some stats. So out of 24 events, we get 4 wrong, 21 right. So yeah, that's ideally what we want is you come with your phone, take a snap, shows you all the colors. So where we were, that's it. Let's start project. Middle of the night for him.
Why do you want different together?
Well, yeah, that's so the other guy who was with us on the team, he said it would be of interest for the industry, and if you can say straight away what kind of event it is, so maybe you can use it out straight away or try to subtract it from your show together later.
So what are the next steps? Getting more physics?
Yeah, exactly. That's right. Because the main transformations will give you a lot of smearing and such. And what I thought maybe we can do is use this smearing as weight for k-means clustering, and then you already know like your events cluster here. So ideally, we want to get completely away from manual inputs. Yeah, and then test real shotgun.
Because you basically gonna think it is together noise screen?
Yeah, generated from the radar domain.
Okay.
So do you see this being used after a survey?
That's actually a good point. It can be used during a survey, just to see what can be improved with acquisition. Yeah, in real time.
How did you find working with Houston?
Awesome. Yeah, a lot of possible help from him. Was first, well, all our team is really basic coders, so and Justin helped a lot. No issues.
How do you adjust when you prepare for the loss of several people from the team? People just cannot continue go on the project. So how do you adjust your work during the hackathon?
How we split the tasks, you mean?
Yeah, but when was it planned that
Song had to leave?
Yeah.
Yeah. Well, we kind of discussed with him the main steps, and then when we agreed on this, he left and we kind of implemented it. But we spent a few hours deciding what project, because we had another project in mind which we disregarded. discarded after 2 hours.
The song was okay. He took early retirement.
Yeah.
Cool, guys. Well, awesome project. Thanks for sharing.
Yeah. Is all set up?
Yep. You need to share your screen.
Yes, yeah.
And keep voting for another minute.
Perfect.
Those who haven't yet. Here before the hackathon.
About a week ago, we found Node, iNode, and looked at some of the models you could generate from that. And we started generating some of those and writing some scripts to read files. But the final training data refreshed yesterday morning. And then the rest of the stuff we did was to actually get the system up. And it's still training on AWS.
So, yeah, we trained overnight the whole model. Yeah. And taking that into account, it does take some time to train it, but if you consider the results after like 8 hours, that's from this morning, so it is still quite fast compared to
the website's recent addition. We're about halfway through an actual demo app, if we didn't have time to make the model in.
Do you anticipate the model will improve? Provide more data sets and train the model?
Yeah, we tried to do some proper forward modeling through shots, the stacking migration. But it was just too basic, so we went simple. But we think if you get that data really clear, the networks can learn all of the nuances and have forward modeling. So we're expecting to get that.
Some green screen modeling to
being able to do this.
Yeah. Those are the 20,000 hours sliced out of the models.
Reverse engineer to work out whether you're working with
I don't know.
Well, we're working with the final specs, right? So I mean, it would be difficult to do this only with near field data.
Because the training data gets, so if we go on the preset domain, we have to cache it somewhere. So far, we'll not be able to answer that. Somewhere in the past.
But it is a black box mapping. There's research where people are trying to reach into the latent spaces and understand. So I don't know if that's more what you're asking.
I think what's important to say is as well that people are actively researching this, especially in particle physics, where you have some physical quantities that you can measure on the outgoing images, like particle energies or the directions they go and check them. So essentially, you have some additional constraints that you could build in to get more realistic images. I think this is just a good first step to show if it's something viable.
I'm guessing the question. Do you see this replacing some processing workflows in the future?
Yeah.
Yeah.
That was a no-brainer.
Awesome job.
Thank you. Really cool. Be interested.
Road, but I think we'll do 2, and then we'll have a short intermission while anyone who needs to can go use the facilities or grab a quick drink or whatever. But you know, if you don't or whatever, then please maybe stay behind so we don't have a massive exodus and then have to gather everyone again. So we'll do 2 more and then that, and then we'll come back for the final 6.
have to treat and water this farm towards the
and then go back to the.
That looks good?
I think so.
I still have a video feed.
Is there what?
There we go.
It's good? Okay, so there's your clock, and Naveen will start the clock when you are ready.
Alright. Okay.
All right, good job.
Just leave your screen.
Okay, don't worry.
It's not my computer. Okay, so hello. We're a team of 5 students in data science and geology. Our goal today was to automate the process of okay, what's that? You're using logs, which are measurements done on wells, and you have to identify each layers of your well. And today, how it's done, you need experts, time, and money to do it. So each interpretation is done manually by an expert. And so we tried to use machine learning in order to automate this process. Right? Okay. We used, as an example, data from an oil field in Alberta, in Canada. We had 200 wells. We had data of 2,000 wells, which we shrank to 700 files thanks to our computer scientists. Well, indeed, 1,300 data files were unusable. And we selected a criterion on this data log, gamma ray, and another one, age, which is computed based on the gamma ray. And we built a model using a logistic regression type of classification. Okay, so after we've trained our machine, those are 2 examples of prediction done by our machine. Here, I don't know if you see back there. Okay, so each color represents 1 layer. So here we have the interpretation done by our quite good, and on 550 training logs and 150 predictions, we had about 75% of match between the expert and our prediction. Which is not using the prediction done by our expert in order to recognize and facilitate the manual qualification of the area study for the prospection, which means doing it, letting the computer learning the data itself without doing our stuff. Thank you. Yeah. So we actually had data of what data did we have? Yeah, we had resistivity, but we didn't use it because, well, the results weren't any better using that. So we just did it on gamma ray measurements, which is a good thing, considering that one testing costs the measurements cost, so we can do it cheaper.
Do you have any ideas how what you could do to improve the prediction?
For sure, if we had the right data, because we just selected the gamma ray, but if we used other measurements, maybe we can train better our machine and try to use some physics, maybe. I'm not keen in physics.
How did the team work together?
How? Well, we just met yesterday, so yesterday, well, we spent all day yesterday to clean our data. I don't know. Yeah. We were one part, there were the geologists teaching us geology, and on the other hand, we have the data scientists doing all the coding, the operational things.
I think your team was entirely composed of students, wasn't it?
Exactly.
Yeah. And you guys just met yesterday?
Yeah.
Yeah, I mean, that's remarkable. Yeah, it was good. Good question though, like with the training data, is there 700 logs with core description in that database? Because we can use the real light with the classes that and so then you predicted other logs and compared the results, right?
Exactly.
So yeah, for those logs, were all of the log description across all 700 the same? So was there like a consistent set of labels that were applied to that?
Well, we built that later and ourselves. So some things you see there, but that's in the table we built that based on the log files we have. So, well, in computer science.
Yeah,
okay.
Water underground. Button.
Yeah.
Share screen. You know where your clock is.
That's
She'll
right.
start that when you start. And that looks good.
Yeah.
Nice. Right, we'll take it away when you like. Okay, I think we're ready. Here we go.
Thank you. Let's go. Right, so Water Underground, a team of 3 people. Martin, who is currently in Port Elizabeth in South Africa. So he joined us remotely, myself, Joseph, and Rabah. And we got some data from a general sponsor who basically started the idea of the project. What can we do with this data that I'm going to present in a minute? And so at the end, it's a very low-key, unpretentious project that I'm going to use to basically demonstrate the first step of a typical data science project. How you download the data, convert text file into data, and get started with visualizing the results and what's in the data, and then maybe build in on trying to go further and do some machine learning, etc. So the outcome really is a set of reusable Jupyter notebooks written in Python that can be used by students or machine learning beginners, etc. And that's really the idea of this presentation. That's the source of the data. It's a Dutch website, a typical cumbersome interface where you can download data by dragging a box around, and it gives you a bunch of text files that you try to analyze and do something with it. So here's an example of such a text file. Very peculiar headers, very difficult to get into the notebook. So we spent a lot of time cleaning and reformatting the data, as you would typically, but it gives us a few functions that can be reused, and we are here to share all that material later. So we managed eventually to get more than 600,000 rows and 464 wells, and then we could do some magics with Python libraries like pandas and matplotlib, and you get some results here. Showing where the wells are, telling you the water table depth. By the way, I should have mentioned that these are groundwater wells, so very shallow wells. And for each well, we've got, over time, over decades of observations, we've got the position of the water table, and we've got also chemistry data that we haven't unfortunately used, but you can see, for example, over 5 decades of observations, the variations of the water table, and this is what happens when you manage to grid the data and create a surface, or you can also see what are the variations and try to analyze spatial variations. And one of the results is this interactive, if I can find it, sorry, it's right there. It's an interactive plot where I've got all my data as surfaces. You can see the wells as little dots, and you can see the variations of the surface, with time from the in the 60s to recent data. You can change interpretation, and all this is done with the widgets in IPython and the Jupyter widget.
Questions?
You were a team of 3. How did the collaboration work with South Africa?
Quite well. I mean, we had the link with the Slack chat room, and we could share files and images. Obviously, it's not easy to get the discussion going, but yeah.
So what's the next step after this?
Yeah, well, obviously, if we can, try to do some predictions or do more clustering. That's one of the ideas that was, at the beginning of the project, trying to see where some wells might, show similar observations in terms of chemistry or water depth, and then see if they evolve with time. So it's a typical 4D data set, really. You've got 3D data and then the time, and see what's the evolution.
So it's just visualization, or what do you want to predict?
Well, it's in Netherlands, close to the seaside. So what the assumption was that there might be seawater intrusions. So we would have been able to see the evolution of the chemistry as the water changes chemistry with time, and then maybe predict how this might change in the future.
So it's a very impressive set of visualizations you've done. Before you go on to predictive footing, you first want to understand whether you can see any kind of connectivity or any kind of trend. How easy would that step be on the way to becoming predictive?
Well, not sure. I mean, you can see how it's relatively sparse in some areas. There are, it's more dense in others. So yeah, there's a lot of work in trying to resample the data. I mean, there is a lot of work trying to resample the data in time and in space. So it's one of the first steps, really. But for
you need to care about space if you're just looking at boreholes. Just let the data speak for itself without placing any spatial constraints.
Well, if you're looking at a single borehole, I guess it would be a 1D problem, but yeah, we were trying to delineate areas and then see how how big they are in space, really.
All right, very cool. Well, thanks a lot, Joseph.
.540, which is only in 6 minutes. But so we'll aim for that. It'll be aspirational. Whatever it is now in 6 minutes. 440.
No, super.
Okay, so you want to maybe go up? Yeah. Well, we're going to get started. I didn't know that was allowed. Yeah, I mean, no, yeah, right. That's one side of that problem. That's reality. Hello everyone. Yes. Hello. Yeah, right. So, I mean, I used to talk yeah. Yeah, I mean, I really like that.
We're approaching some turbulence.
Mec, et même il y a des
to share the screen. It should work.
Looks good. You're there. There it is.
Okay, great. So then,
And you're all set. And Marine there has the clock.
I'll tell her.
You see her? Voila. And you're all set.
I'm pretty sure.
Quieten everyone down for you. All good. So there's the clock. And okay, everyone. I think we are ready. I'll go and find these people. Hopefully nothing's happened to them. And take it away.
Okay. Good afternoon, everyone. I'm very glad to be here and present this project. Also, our Ops Noise team. So I'm very glad also to work with these guys that they did a very hard work. So we have Jonathan, that is a geoscientist. Dorian, he's doing data science masters. Lou, she's doing data science master also. Gian, sorry, French. He's doing geoscience also, and myself, I'm doing my PhD on geoscience. So the idea is to we want to reduce costs in oil and gas explorations using geophysics. Now, okay.
I'll do it.
So, especially we have some traditional methods in order to monitor our oil fields, but this is very inconvenient. In order to get best results, getting monitoring, we do active service. So we are in the ocean. We send some boats, and we acquire a very expensive, that is millions of dollars survey in order to have a very nice image, and then take some actions in the oil field. However, this is very expensive, as I said, and we lack also of low frequency. That is very important for our imaging. So we know that, for example, BP have some OBS, that is ocean bottom seismometers in the Norway Sea. And the idea is to, because these are permanent receptors at the ocean floor, we can record noise all the time. The idea is to use this noise to help the people in the production to see if we can still exploit oil from this idea, from this field, sorry. So the idea was to, okay, we know some people that have already get signal from noise, but they spend the whole thesis 3 years trying to process the data and reduce the noise and image all these. So we planned to do machine learning to work at the same time with the geophysicists and try to learn what the geophysicist is doing with this noise. So with this, we can implement fast actions in our oil field. For example, is we see that well, we can measure also some quantities. Is we have the good seismic imaging. The idea is to, we have some noise and we want to filter as geophysicists can do it with some analysis. The idea is to maximize the current energy that is coming from the oil reservoir. So those are our results. I will first explain. This is how the survey looks like. We have our reservoir here in the subsurface, and we have ocean bottom that is permanent. So this is what we should got with the Malmuzzi model. I did a very good, very fast imaging. This is what we should get. I prepared the noise in order to, if I stack everything, I still have some idea of the imaging. And this is what we got. found some traces because we lack of a computing method. So we see that the blue ones are the predicted one is the blue ones they should correlate, and the yellow one it should not correlate because it's only noise.
Okay. Question: how did you split up the work between the teams? Did you guys know each other before?
So we prepared a meeting in order to discuss some projects last Saturday. Yeah. So we proposed some projects, and I came with this idea and what I did in my master. I didn't do noise imaging, but I knew how to do virtual receivers theory, that is convert a noise to redatum the data to where the receivers are. So that's why I can convert sources into receivers. That's the idea. And then we try to process the noise in order to have a very clean training set with our geophysicists, Jonathan and Jan. And then we explain the geophysics to our young colleagues, and that once they learn what is the good trace and what is not a good trace to filter, they implement some methods to test how the features in our matrix are, what is the behavior of these features, taking into account the processing of geophysicists.
How much do you think you can speed up the existing workflow, or how much can you reduce the resources needed to do that?
Well, the main thing here is that we know that the philosophy is to get a very good image from this reservoir, because we want to take actions in that. So the idea is to get not only the information from noise, but also with the active survey, and try to decide is, for example, is we don't detect any change in the noise. The noise will record every day, and we can get image or coherent noise from this coherent energy from this. We can know is we are prepared to do active survey or not. For example, this is not the case. We can save some millions of dollars.
Yeah, because it's a full-time surveying thing. You can basically have a full 3D blocks of the zone every day instead of every 2 years by regular boats and seismic surveys.
How long would you expect to monitor passively to get a quality image that is comparable to
the simulation we did was 6 hours, but few months it's
yeah, for the work that we, people have done in academia, they need some 6 months of noise in order to clean this noise in order to get a good image from that. So we want to then, after this 6 months of processing, interacting with the machine learning will learn how to, algorithm will learn how to do this.
Awesome, very cool, guys. Thanks a lot.
On parle français. The killer.
You want to have one of these Mac Thunderbolt, I guess? One is coming from somewhere.
Okay.
Yeah, anyway, sorry. Thanks, Dave.
Maybe I don't want to finish.
Okay, Graham, so the hangout didn't work out there, but we are going to carry on. Naveen, almost? Okay, thanks everyone. Take it away.
Hi everyone. Today we are going to talk about S3 classification with the GeoRock dataset. So as we know, all of the rocks are classified by diagram. It could be magmatic, sedimentary, and even metamorphism rock. So we classify them by the composition of the mineralogical inside of each rock. So we wanted to have an algorithm with this data that we collected from GeoRock. So we took all of these samples, and so we put all of the data on the Python, and we have all of for each rock we have all of these elements, mineralogical composition, and we can detect which rock is it by the mineralogical. And also we wanted to do the same thing with the localization and its environment. Like this, we can put it together, and at the end, for example, from some society as the mining society companies, we can have an idea of the location of the ore body. Okay, so now concerning the machine learning pipeline, we had two machine learning tasks. So as Carl said, the main part at the beginning of the project was to be able to classify multiple types of rocks based on their chemistry. So this involved a few steps, usual steps like selection in engineering. Then we had to select for the model. We ended up using random forest because it gave us the best results. And after that, we were able to gain 5 more points of accuracy, moving from random forest to a newer kind of random forest that's called refined random forest. Okay, so that was the first part.
classification. We'll talk about it later. The second part was clustering. What we try to do is try to find chemical structure within same type of rock. Like for the same type of rock, we try to determine whether we could find different chemical structures, because this could give insights to geologists as to what happened to the rocks in the past and other kind of information useful for the job. Now, as for the results, for the classification part, what we can see on this diagram is that the natural repartition of the types of rocks is more or less the same as the repartition given by our prediction. So this gives us a first insight of the fact that our results were coherent to begin with. Now we're going to focus on the accuracy by type of rock. What you can see in this diagram is that more or less we are more or less most of the time over 80% of accuracy, and all types of rock considered together, we managed to reach almost 90% of accuracy, mostly by considering the location of the rocks and changing the model from the first to the second one. Okay, so this is the model that tells us which chemical element is the most important to identify a rock. So the most important one is silica, for instance, and the second one and the other. Okay. So now this is an example of clustering. So we can see that for the basalt type, there are two kinds of chemical structures that are very different, and this allows us to define the classes into even more precise classes to be used by the geologists.
So as I said before, so we have each rock has its own the mineralogical composition, and so we wanted to combine this with the environment, so that there's each environment that is on also mineralogical and on the texture. And so if you put the rock with the environment at the same time, we can identify what kind of rock we can find in this case, what kind of rock we can find, and even with the elements that we are looking for. For example, if you want to have the old deposit, so you are searching for maybe this type of element precisely. And also, as I forgot to say, we applied this for volcanical rock because that was from the data, but also we wanted to do, if you can do it for sedimentary or whatever you want.
How many of you on the team?
We are 5 on the team, so we have 3% that they are studying geosciences, and 2 people they are making machine learning. I think it's like this. And so we discuss together each other to mix our skills. We have more about geosciences, so they make more about programming, and we have fun a good thing. I think it's a good thing.
It was interesting because 2 of us only had knowledge about machine learning and pretty much nothing knowledge. So you understand, the other 3 students only knew things about geosciences. So at first it was really difficult to keep on talking and eventually understand each other, but it was interesting to make use of each member's skills to do something that could be of use maybe to someone in the field.
Well done for starting with igneous metrology, because I think you've got fewer degrees of freedom when you're working with sedimentary metrology. I think it's much easier to then concentrate on the machine learning workflow. Were you working with rock descriptions written down by some idiot metrologists, or were you using actual mass spectra?
At first, we were using both 2 kinds of features. Like we have the proportions of the different chemical elements, and also some descriptions made by experts. But after a while, we decided to start making use of those descriptions because we assume that that wasn't the purpose of an algorithm to make use of the work of a human. So we only kept the proportions of the chemical elements in order to make it.
Awesome. Well, thanks a lot. Great project. I can get that. No.
Bogfix, you're up.
Oh, yeah. Okay, that's very fine. Whatever. Smaller. Okay, so you know the time. Yeah. So happy. I think we're ready to go. Okay, take it away, Rob.
Okay, so hi everybody. This is the Logfix team, and they're actually following on from the first talk. You said you wanted to fix missing log sections. Well, this is one of the things we tried to address. We're not petrophysicists, so please bear with us. So if you have this kind of problem, you can come to Logfix. So basically, we're using the same data set again up in the Athabasca Basin in Canada. We're looking at a simple triple combo situation. For those that don't know, the gamma ray is giving us pathology, the resistivity is giving us hydrocarbon charge, and the neutron density is giving us the type of hydrocarbon. Here we have an example of some of the wells, or one of the wells that we had in the data set, and let's just assume for the sake of argument that we're missing a section of resistivity. I'm not going to go into the details of why or if resistivity is a good example, but this is just to test the model. Now, the rig up here is in Kurdistan, it's not Canada, but basically it's to remind me to tell you that these things are very expensive to run, and therefore if we have a missing log, what do we do? So we came up with a couple of solutions.
The first solution is based on the idea that there is a pattern called pattern. So when you have an lithology, the next one would be normally similar, it could be the same, and there are only a certain probability that you move to another one. So here we have the transition, the possible transition from one lithology to another with that probability. This was entirely created from the data that we have from Subsurface. The idea is this model can then be used with the geologists to tune it, to check it, and to make it fit with the data that we get from the field. So with this, we reconstruct the lithology, and with the based on the logs that we have at hand, and with the logs and the lithology, we can then recreate the resistivity that we have here, and you can see in red the true value, and in green the one that was estimated from a simple support vector machine that uses the lithology on the logs. And we had a second solution.
Yeah, so the second solution is based on a nearest neighbors model. What we do, imagine we have a well that missed some resistivity data. What we do is first estimation of the resistivity with the nearest wells of this well. are the same depth, because we assumed that stacks are continuous. So that's the first estimation. And then we use gamma log, mechanicity, etc. The logs we have, and we use a super vector machine to do a regression and have a final estimation of the resistance.
And then, so finally, why are we doing this? Basically, the idea would be to minimize costly log reruns if you've missed a log or whatever. QC your existing data. Here we're looking at a patch of missing data, but one of the ideas is that you could also QC data where you've got erroneous values. Reduce cost, improve reservoir modeling, and speed up data rooms as well. Having done data rooms like many people, if you have a huge data set and you want to run through it quickly, this approach might be useful. And that'll be it. How did you form the team? Well, we met for the first time yesterday, and actually two of them knew each other before. And well, I guess I'm a geologist, virtually no coding. We've got a couple of really good coders. We've got mathematicians and so on. And well, basically, we didn't know what we were going to do. Just cracked at it, and this is what we have.
What are your next steps?
If we were to continue this, we'd have to, well, basically check the other logs as well, tune the data, check the other logs, because I mentioned briefly that resistivity might not be the best log to be doing this on, because we're using lithology logs to look at the fluid response. So, yeah, those would be, for me, the next things to look at. And obviously then deploy this to an app. Yes, sorry.
It looked to me like some mythologies, the prediction was good. Other mythologies wasn't. How can you explain which mythologies are causing you to get an idea?
On that particular data set, no. However, having I don't know the Athabasca Basin, but thanks to Wikipedia, I know there's a bunch of hot sands in there as well. So I know that potentially there's volcanites. Potentially you could have some lithological signals that we're not capturing as well. I don't know more than that, but that would be one explanation.
So beyond Athabasca, where you have lost many wells, what other areas?
I guess the value, and please cut me, but basically the value is for large data sets. So data sets where you have a lot of hundreds, literally, of wells with the kind of situation we were talking about before. We've got just too much data to look at one well at a time. We'll get a petrophysicist to look at each well. I mean, you pay $1,200 a day to a petrophysicist on this kind of data set. It's going to make a fortune, and you won't have the answer you want. So, large data sets.
I think you need similar stacking patterns in the sequences in all your basins. At least not so different. Carbonate would be a bit more difficult.
There's another, just bouncing on that as well. I mean, we're looking, again, I don't know the Athabasca Basin much, but Matt told us that there's not much fault here either. So it's potentially, you'd have to QC your basin to know.
Awesome. Fantastic job. Okay, we find out who's let's do this. Probably can't see it. I can. Try and get me. Yeah, good. Water magical. Water magical. Not allowed to again.
Okay, Gmail address. Log into Hangout. Just open Hangout app.
Louis.Poirier.
Spell it again.
Oh God.
No major health facilities.
Get rid of that. Cool, you want to answer? The green one.
This one?
Yeah. Share, I think. Is, yeah, with whatever you like.
Sweet. Okay.
Looks good. Yeah. Okay, awesome. So basically, ready when you are.
It's cool. Okay.
Do you want to come back over rounds before terrible things happen? And you know your clock is over there. All right, take it away, Louis.
Okay. Hi, I'm representing the team Automagical here, made of Maggie, Jonas, myself, Georg, and Bjorn. And we focused on 3D modeling using machine learning. So the idea is that 3D models are awesome. They can be used for visualization, understanding your reservoir, or like whatever is going on under the ground, and also interpreting what you can do with it. Fortunately, they are usually constrained by like the fact that you don't have much data. You like have some information, but it's not representing the entire area. And workflows, and I'm taking that from people that actually do that, is challenging, time-consuming, and usually boring. So the idea is, let's use machine learning to actually solve this problem. And the idea that we want to do is to use a model to make it faster and more consistent also. And to also try to share knowledge from one model, one geophysical model to, or multiple geophysical model to apply it to like a new one. To do so, we are basically taking a 3D model, or like an idea of a 3D model area. We slice it in different areas. So we have a geologist that would actually come up with like a real cross-section of certain areas. Can be in any direction you want. You can also have some kind of like drilling information. And the idea is you are going to try to interpolate what's going on in between. So instead of using an explicit method to like know what's going on between those slices, we're going to try to use machine learning to propagate the information between them. So we train on the available slices. So in our case, we had a 3D model that had been developed already, and we sliced certain areas. We kept some aside for training, and we kept some aside for testing. And the idea is we're going to predict what is a rock type based on the XYZ coordinates of the point in which we are, and recreate certain slices. The prediction is able to recreate any virtual slice we want, and if we make enough, then we have a 3D model. The comparison today is done as like on a pixel by pixel comparison. We can talk about that. There are way better things that we can think about. In terms of achievements, we were able to like fully automate that. So from beginning to end, simple Python scripts, but like it works from beginning to end, from a shapefile all the way, like that comes from like your reservoir, all the way to a function that is able to generate all of your slices. We got 97% accuracy. I'm expecting a question on that one. But it's actually the number that came out. And the it's able to basically interpolate realistically some, I would say, simple geologies today. Simple means that if we actually have some faults and things that actually happen in real life, we start losing some accuracy. The idea, again, is that the model is able to learn from slices in any direction. In this case, we actually just took them parallel, but you can take advantage of like slices that would go across. So again, we try to put all of those slices that we generated. So here you have the real one, here you have the predicted one, and here you have like the delta between the two visualized. We put all of that into a 3D model in ParaView and like try to turn it. This is nice. On the side, you can see that like things starts like going a little bit out of whack, but overall, like we do get some interesting information. Very quickly, the immediate next step, we want to be able to train the model on better data. The idea is like we are missing a layer at the top that like made our life miserable. We're missing things. We want to develop a better loss function, and finally, we would like to train as a sequence, so like my information as I move through my slice.
What actually takes time to build the models is the tricky part where you have faults and things like that. So what's the next step to deal with this type of
So I don't think that the approach is necessarily like not capable of handling faults. The reason we had issues with faults is because the data we had would break in those sections, and so like the original data we worked with was not good enough to do that. The model itself should be able to understand that fault is like a new section is coming, as long as like my cross section is kind of making that fault appear, and find the direction of the fault as we move along. The regionality of the data should work on that one. So having better data would apply to that would be something I actually really would like to do, because I think that we can get something interesting. This is not intended to replace the geologist by any means. It's more intended to like start the process, and then like you can fine tune what you want, and so you gain like 90% of your work.
Yeah, just made my question. I was going to say, do you see this as something that augments the workflow to improve the speed of the workflow?
Yeah, augment the speed, not replace the expertise by any means. I don't think machine learning does that in any case.
What were the skills on your team or your background?
That's interesting. So Maggie here is a geologist. The team here, Georg, Bjorn, and Jonas are more like working on the storing of 3D models. So they were the origin of the data, and they were able to like extract the different slices. And I'm doing data science for a living. So good mix.
You get a confidence response as well.
We did not do that work yet, but that would be next step.
Be able to calibrate it also with seismic data, so with the whole morphology.
I think that would be interesting because here we don't use any information about like what exact rock it is. We just use information about like the transition between the different layers. So we could make some assumptions about like, okay, have a stack like this one, like the seismic information interpreted could give me some additional information. Not guaranteed, but cool.
All right,
thank
you.
Good.
Great job.
Eyes on the rocks.
Okay, let's go.
Did somebody step on it?
Yeah.
Something didn't compile or what? Gonna pick your name eventually. Yeah. Yeah, exactly.
Yeah, we put a win on the roll and crash. Yeah, that worked on the machine. I've never done something like this before. I think I know how to do it differently. You were grabbing some images, right? You were grabbing some images. Yeah.
You okay? Yeah, no, it's okay then. That's it. Looks like you're good, right, Graham? Looks good. Okay, I think we're all set.
Automatically, that can save, a lot of hours of subject matter experts just sorting their documents. In this question, are there some rocks in my log can be solved? It's open the possibility to reply to a lot of some other. Is there a VSP in my document? Is there a gas show in my composite logs? Is there whatever we want? Are there common image in my reports and so on and so on and so on?
Okay, so the implementation, the method that we use to detect whether it was or there wasn't logged apologies in a log was a convolutional neural network. So show off the convolutional neural network. It's the same as object identification recognition, but this time we're just trying to identify the single problem, which was there or not, was there or was there not logical logs inside the log. So a background, in terms of the background, we had a team of known coders. So there's 3 of us that have never written a line in Python before this weekend. And then we're all from a geosciences background, so it's not a very diverse group. So how do we pull together over the weekend and produce something in terms of the neural network that outputs this great idea? So we had a lot of help in terms of we used the storage from the Amazon Web Services, and then the implementation of the neural network was by NVIDIA Digits. I'd like to thank Francois and Victor for that, and helping us get that set up. So going forward, there were some issues to solve in terms of the data preparation. We had so our log images are not exactly like cats and dogs. We have very long kind of issues there. So there's a lot of issues with the aspect ratio, resolution, that sort of thing. So we have to normalize the data before we input it into our neural network. So to do that, we segmented it, keeping the aspect ratio the same, and then we input it into the neural network. So does it work? And the answer is it does work. The data set that we use is very small. We only use 70 logs. But the segmentation, we upped it to, I think, 1,000 input images, which still is very small in terms of convolutional neural network. But going forward, we've got 70% accuracy. So there's an expanded data set. Hopefully, we could take it further and increase that classification.
Yes, so yes, probably the learning model can be improved. But what our conclusion is that, though, thanks to the learning model, we can help the whole company to reply to the question, where is hole in my documents, before they go to find it in the subsurface.
So how was it like discovering Python?
Steep learning.
So how many of you are on the team?
So there's 4 of us, so I've not been down. So yeah.
And had you met before the hackathon? Or?
Yeah, so 3 of us are from the University of Leeds doing an MSc.
We met together yesterday morning. Excellent. So what next?
Well, if we continue to work on it, and to be possible to do, is first to improve the learning model. You know, you have to make it more mature, which is a result is one of the best we get. So we can improve it. And also, we have been working fast. You know, instead to spend a lot of time preparing the data, you know, extracting the little column for the training and so on, we just split the image in few boxes of 500 pixels, 500 pixels. We open everything a little, and what is not the little. So I think if we focus on just the little, it will be possible not only to find is there a little column, but which kind of works are in my documents. So if somebody is looking for, I don't know, a sort layer with logs, find these logs, it's possible, to reply to this question and provide to you this document, only the one having this sort representation.
And so I think taking forward some frameworks that you can set as an object mythology, and say you've got an image for a symbol for a gas show, that sort of thing. There won't be like a big set to take that forward and say, oh, try and identify that.
What's fantastic is possible to do that without any programmation and without just using the cloud.
We've got time for another question.
My question is for the master students. Do you feel like keep on working on this? On this topic for your project?
Yeah. I think the support is fantastic. It's a good way.
At this stage,
yeah. I think one of the students has got a machine learning dissertation, so he's got quite lots of eyebar this weekend.
I was it was definitely beneficial for me to get to and definitely using some of the higher packages as well, being able to sort of bring up interface, really like improve your learning curve by not having to get tracked down in the back end and really actually focus on machine learning. I like to that's really cool.
The learning is that. Where did you learn on?
It's come from the OTA UK part of it. Few of them, and some of them came from New Zealand. That's fine. It was a small data set. We have just prepared that yesterday morning, and again, it could be maybe improved kind of preparation. It's writing exactly what.
Going forward, you want to see that you have more works to choose.
We have mixed together color logs, some also in grayscale, that all together, and
but they have been tagged. They have been tagged by.
Yes, we have bias specialists tagged by us.
That's a good start.
But I mean, yeah.
I'd like to be setting the question on that, so feel free to refresh and keep voting on. Leave it open for a couple more minutes, so please do go ahead and vote.
Last one.
I hope you are.
How do I? Yeah, here's it. The green one. Yeah, that'll just do your entire screen, I think. Well, wait, there's
Okay,
like...
let me mirror it first.
Yeah, awesome. Ubuntu is good at trying to help you.
Yeah.
Okay.
Should I just move?
Yes. He hasn't hit share yet. I think it's going to be all right.
Yep.
It's good. Marine is ready. You see the clock?
All right. So I'm going to get started. It's not our fault. And our project is about feature recognition using machine learning. So geophysicists spend a lot of time trying to interpret seismic sections, looking at seismic sections, and trying to identify geological features. So the idea behind this project was trying to do that in an automatic way using machine learning. So we built a little website to show us what we did. So what we implemented was an image processing inspired Haar cascade type filter. And with that, we are able to identify geological features in seismic images. But before we do that, we actually had to generate a bunch of training sets, a bunch of training data, and use that to train our Haar cascades. So the first thing that we did is we built from the ground up a convolutional based model to generate our images. Then we took these images and we trained them using some software that we also implemented based on libraries to implement these Haar cascades. And then finally, we built this web app, which I'm going to show you now, in order to interpret these images. So let's give that a go. So first I'm going to upload some files. But the first one that I want to show is identification of faces and a bottle as well. So I'm going to show that in a normal image. And this is usually what's done in image recognition using humans as models. And I'm going to show Claire here with a bottle. And it's worked. It's identified her face, put a little dot on her nose. It also identified a bottle. So basically, this is just what it's usually done. And now what we want to do is we want to use this on seismic data. So we're going to input a seismic section that we generated, but we obviously didn't use to train. And since seismic data is completely different from faces, we have to give different parameters in order to be able to interpret this kind of image. So we put these little tuning parameters here that people can give it a go later and try it out. So, okay, so we've managed to identify these little traps that we inputted. And let's see if we can also identify this fault that's going across our image. And again, faults are different than traps, so we have to do a little playing around with some of these parameters to be able to detect them. So let's see how that goes. We get our fault as well. So ideally, afterwards, when all this is done and you have a lot of images, then you can put in a library, which is obviously not filled yet. And you have basically a library of interpreted images. And you can also use the software that we put in the backend to generate all the training models. So if you like what you saw, thank all these people as well. Obviously, I'm just the presenting guy. And please, obviously, come and fork us on GitHub. And you can also use our website, which won't be available forever. So you can also get it from our GitHub. So thank you very much. And
so how is the team set up? Do you guys know each other before, or?
Yeah, so most of us know each other.
I didn't know anyone.
Except
Slack recruit.
Yeah.
Yeah. So they come from the same university, and
I knew them already, so we were planning to attend this, so we chatted, and then he jumped on the train through the chat. He saw that he was interested in this, and he asked to join, and then worked out very well.
And what type of profiles and competencies do you have in the team?
We are all geophysicists by background, but we all like to code, I would say.
Yeah, we're all computational geophysicists.
Well, amateur coders.
More computation geophysicists.
Yeah.
I know that pattern recognition in seismic data has been around for decades. What do you think that your approach makes different?
Claire?
We just thought
it doesn't.
We just thought this would be a really fun project to bring. So I mean, you use facial recognition all the time. Facebook's doing it. I mean, you can even now do it on your images when you upload a file to your Windows computer. It will ask if you want to tag a face. So this is the software behind facial recognition. We thought this would be really fun to try out and see if you could also apply it to seismic.
I was going to say, did you try the fault detection on any real seismic?
No,
not yet.
Seismic, yeah.
So obviously, ideally, synthetic seismic looks a lot different than real seismic. So ideally,
beautiful.
Well, yeah. So ideally, you'd be able to get from databases that companies obviously have of interpreted fields and things like that, and you would use that to train models that you can use on new fields. But the interesting thing is that these are obviously they're local algorithms, and depending on how you train them, you only need to know a special location where the fault is, and if you don't need the same field to train to use in another field, basically.
But will you be able to generate a training database in this weekend from real seismic data? So that.
But I think in a big company which has a lot of database matching seismic and interpretive faults, maybe that would be a great database to throw in.
And more than 2 days.
More than 2 days. Yeah.
I mean, even the training of the cascades, to get a solid training, you're throwing in 2,000 positive images and 1,000 negative at least. And that's a lot of training. It has to be done overnight, really. For 2 days, you have one night.
How do you think this will, or this could accelerate the workflow of an interpreter?
Well, interpreters is sometimes maybe 10,000 lines, and you could do a few and then hope that an interpolation does some of the job, but you could also get some information out of these and start from the locations where has been prompted, rather than go randomly in one section to start.
And not just a human interpreter as well. I mean, these kinds of algorithms, the Haar cascades in particular, they're usually used as kind of some pre-processing, and you look at some particular parts of the image. For example, the fault one, you can then throw a much more sophisticated algorithm to actually pick out the fault. Then you don't have to look at the global image. If you pick some regions, and you can then use that to throw your better algorithm out.
Would you like a continuous learning of this?
Yeah,
so
yeah.
It says that's wrong here, but do it this way.
Oh yeah, definitely.
Yeah, you could relabel and give
There will be a new.
We should collaborate with Pick This.
It's more work than the interpreter.
Please. Very cool.
It depends.
Thanks a lot, guys. Fascinating project. Let's give all of yourselves another round of applause, because that was all awesome. And I also just want to kind of recognize the people, especially who were presenting in their second language, or maybe even their third or fourth language, after Python and like really fantastic job. I've done that myself too in Norway, and I know it just adds another dimension to the kind of the stress. So good job, everyone. Fantastic. So now the stress starts for the judges. They're going to go up to the deliberation chamber, from which they will not be released until decisions have been made and arm wrestling has been completed. And we are going to hang out and maybe kill down a bear outside of this room. It's so nice when you walk outside. And we'll aim to reconvene. I mean, we're basically going to give them kind of the time they need. It's probably going to be about 20 minutes. So let's aim for 6:10 to come back in here and hear from them. So thanks everyone. Good job.
Deliberation, like
Non, le voyez pas comme ça. Moi, c'est
oui, non, mais ça n'a aucun sens. Ce sera pas rentable. Merci.
Yeah, I'm going to do I tried to count.
Yeah, there's a couple of like little projects.
Are there? When you're on? Okay.
Yeah. I mean, I don't think we met. I'm Graham. Okay, great. Yeah. Did you just come today?
Yeah.
Okay. Yeah.
Just the right. Let's use 5.
Glad you could make it. Did you have fun?
Yeah. Good. So this kind of thing. Yeah, it was the story, but we added a bunch of complexity.
So far, perfect. Perfect.
Yeah.
Excellent.
So,
I have to admit, Willie would have liked to be here, and he said he couldn't be, so he just said, "Oh, you really need to talk about Eagles?
Eagle, yeah.
Oh, you've spoken to Eagle?
No, I haven't spoken to him, just
like that teamwork, okay, so he's my boss.
Okay, but I think is he coming to the END?
No, no. So, yeah, it's interesting to look at. Is it, yeah. I don't know where you are.
Oh, yeah,
You hinted that you've got some ideas. But...
Yeah, right. Yeah. So I feel like we've committed to doing something.
Right.
We don't necessarily know what something is.
Nice to meet you. You just came to the presentation.
I'm interested in.
Excellent.
I mean, sad to say, like, we just got to the end of this and I'm sort of thinking,
it's pretty amazing.
Really successful, like, maybe we have repeated
some of these,
like
as
this.
I mentioned,
We tweaked a bit and tweaked.
It's really impressive. Thanks for coming in.
Oh, yeah.
Did you find your way to this coffee and water? Okay.
But then there's some other.
Got it. Well, it was nice to meet you.
Yeah.
Thanks for coming.
Scaling the reach, and I kind of wonder if we can bring it outside of the room and phone out even more. Actually, even more people at the conference, so that 500 people can experience it, not just sort of 85. And I got some ideas about what that should look like. I don't know if next year's the year to try that. And another angle too that we haven't, like, doing this with Total was maybe an opportunity to explore this, so I felt like we were already innovating on that front to leave it alone. But there is the thought too that we could crystallize the sort of next steps to the commercial impact by involving basically things like, I don't know, like we'll provide problems that we're interested in, right? Maybe provide a little bit of data and maybe even a bit of code or an API, and maybe at the end it's like, not only are we recognizing teams of efforts and stuff, but we've identified
I think so. I would actually
accelerate
sorry, Neil, I'm just hanging on your conversation here, so I just wanted to say to you, great speech, and I'll take the opportunity to give you my notes. So,
great. Yeah, cheers.
I guess I'll see you tomorrow.
Okay. Yeah, we'll be blogging about what happens next. Because, well, we're giving out prizes for 5 so you can find out who prevails. Okay. Cheers. Excellent. Yeah. So anyway, there's a few ideas floating around.
Just get in touch with us about it, because I can't speak for the people who have the budget.
No, of course.
Things, right? But I do know that MESC at the moment is. We're splitting up the MESC group. MESC Oil is trying to get investment, making a big push to say we're small than you are a year ago. A small, innovative company. We do some very selective R&D work. So it kind of fits in with that message. And I don't know, we haven't really, the last couple of years, we haven't gone as far as paying for it, but might do I'm not sure. But this kind of event might be very interesting for innovation stuff. So we might be able to do something. And at the same time, we've been talking about seeing some of our little random utilities, so that could be a time to just sort of throw out a few little Python libraries and say this is what they do. And
right.
You do anything with them. Improve them or whatever. I don't know.
Well, that again, so there's another angle that we've never really explored, which is the sort of deliberate improvement of a particular tool set, almost like a sprint.
I think it's probably more interesting to take something and do something new with it, rather than just tweaking something that exists. But I don't know.
I mean, the beauty of these events is that you just have no idea what's out there, and people are so creative and the stuff they turn up with, or the backgrounds are so diverse that and people are quite inspirational. They're like, oh, I've got these 2 days they're doing for with people in the network, so there's sort of like something to use, and it's all outside. So people are pretty adventurous with their so in many ways, good to know you need to the container.
You've done a few of them now, so
it's
the model that works. It's a lot of it, and increasing interesting.
So, anyway, it's
I'll let you get on.
Yeah, I'm going to go and
fairly busy.
See how the judges are getting on.
Thank you.
What's the best way to find you, by the way, if I want to chat again? You don't have a booth, but you'll be at the...
I'm at the workshop tomorrow around bid science. Same email address I can pick up.
Sounds good. Cheers.
Thank you.
Yes, green.
So let's just get rid of Slack.
Oh, just come over to the side and it will come back. And then you can just choose PowerPoint if you want, or do the whole. Are you going to show the data?
Only in boxeted format.
Okay, cool.
Anonymized.
Oh, right,
so no
right.
team names, no judge names.
That's very
Just,
cool.
This
I
is the
love it.
data.
Yeah, awesome. So yeah, let's plug in. You can go for that. And so I'm going to hand over to David Holmes of Dell EMC, a long-time supporter of this event. And he was kind enough to kind of do the judge wrangling today because the other guys were kind of new to the process. Well, actually, there was a bit of process today, so congrats on that. And with that, I'll hand over to David. Let me just turn this back on for you, and you take it away, David. I'll sort that out. It was off. Sorry. It'll come in.
Okay, ladies and gentlemen, the moment you've all been waiting for, the prize ceremony. I'd just like to say, for me, this has been an amazing couple of days, as it usually is. This has been a real breakout year for the hackathon. I've been to a couple of these, and they're always good fun, but it's been incredible to see this kind of supersized and the level of enthusiasm that's been in the room. I think it's beholden on me to say a few words about Agile Geoscience. They're a small little outfit based in Canada who put far more into the community than the size of their organization might have you think. These guys are quite incredible for the amount of time and effort that they put into this. Now, they're not a big commercial event organizer. They're not making $500,000 out of running this event. They do it because they love it, because they're passionate about it, and because they want to grow the the community. And I think they're amazing guys. You know, for somebody like me, you know, like I get paid if I show up to this or I don't show up to this, but these guys give up a huge amount of their time and effort to put these events on. I think it's incredible what they've achieved over the last few years in building these events. So first of all, a huge round of applause to the guys from Agile. And I think lots of people going to making these events happen, but I think we have to also recognize the contribution that Total have made, providing these amazing facilities, giving us the ability to scale up this event to something that I've not seen before. So thanks to everyone from Total for all of the efforts they've put in and for the amazing space they've given us. So thanks to Total. I know what you're all saying. Just crack on, prizes, please. Now we've been diligent. The judges have done our own little bit of analytics. It's a quick preview of an anonymized version of the results. And so what we're going to do is hopefully the team over to the left know exactly which prizes go with exactly which awards. But I have the crib notes here. Without further ado, I'm going to do the first one. This is the teamwork prize. I'm very happy to announce that the prize goes to La La Land. That's Accenture for you. No, seriously, the prize for teamwork goes to Logfix. This is the point where the Logfix team all come to the front of the room. So guys, if you want to go and stand on that side. And for any remote collaborators, we'll figure out some way to appropriately reward them. So yeah, once again, well done, guys. Congratulations. Well done. Thank you. Well done, mate.
More teamwork.
So Logfix have got a collection of mini drones and some other assorted goodies that they can play with. So next up, I'd like to invite Matthias to give the award for presentation.
Yes, thank you, David. Thanks all. First of all, I must say I was really impressed. This first time I hackathon here as a judge, as a jury, and so what all of you have delivered was outstanding, just in so short time. So take that can-do attitude further on, and you will have an exciting time ahead of you. Continue to have an exciting time ahead of you. Now, everything needs to be presented, right? And in order to present something right, I will announce the prize first, and that is in noise-cancellating headphones, because that's what you really need, whether you're virtual or real presenting. You don't want noise in the room, right? So now that people can talk as much as you like, you can still present. Yeah? And the winner for that best presentation is, and the jury has talked long about this, and I must say it's not my fault. It's not my fault.
Stand pretty for 3 seconds.
Thank you. Oh wait, let me move all together. Thanks.
Oh, one more time.
Okay, I'd like to invite up Eve to do the presentation for originality. Do you remember who won?
Yeah. Okay. So thank you very much for to everybody for coming up and spending these two days at Total. I was really impressed. I stopped by yesterday and I saw everybody working, so I didn't want to disturb anybody. And today I was really impressed by the quality of your presentations. All the 13 teams, you really did a great job, and I'm really glad to participate to this event. So originality, that's the third prize. I guess the winning team is Logs on the Rocks. And the prize are connected watches. Is that right?
Yeah.
Thank you very much. Yeah. Smile for me, please. 3, 2, 1.
Okay, get serious now. This is where the big buck potential comes in. So, Frederick, if you could come and present the prize for commercial potential.
Well, I won't let any suspense, because the choice was quite crystal clear, and the prize is given to Scene Section. You're winning from books.
Oh, wow.
Oh, thank you.
Thank you.
Congratulations. Thank you.
Thank you. Where's team number?
Joyce is gone. Yeah, we have two.
All right, smile like it's 5.
Good smile. Yeah, so Simon and Jan had to leave.
So you can train.
Yeah. Well, thank you. Thank you very much. Good job, guys.
Okay, and finally, I'd like to invite Arnaud to come and say a few words and give the prize for execution.
So first of all, I'd like to thank everyone for these 3 days actually with the boot camp. They've been really amazing. When we first thought about organizing a hackathon, that was the late December. We didn't really know what we got into, and then we came up. We got into Agile Scientific, and I think the collaboration has been really great. And we're looking forward to further ones. So I think this has been really a good collaboration to set up this event. So thanks for that. Now, I hope that you had lots of fun, that you had lots of learning as well on the 2 days. Now for the last prize, for the execution, I'm calling the Gangster team. Not anymore. Okay. So before we split up tonight, there's another drink and we have some time to spend together to close this event. See you next year sometime.